Thank you very much, and good morning. In fact, there are a lot of similarities between climate sciences, I think, and what ASPO is doing. Nevertheless, I first just want to take you through climate science. I realize that most of you will know most of it, but I'm also aware that probably there's very different opinions on climate and the importance of climate science in this room. Bear with me if I just maybe repeat something you do know. The first thing that is very obvious, climate has always been changing. You see here climate change, the blue line is temperature over the last 400,000 years. And obviously there have been changes. There have been considerable changes, and we do understand why it happened. These 100,000-year periods of change are due to the eccentricity of the circuit of the Earth around the Sun. Then we have something like 41,000-year cycle, which is due to the axial tilt of the Earth. And we have something like 22,000-year cycle, which is due to the precision movement around this axis. These changes are quite obvious these cycles are quite obvious in the past. But in themselves, they don't explain the temperature change. But before I go into that, let's look at what these changes would mean for the future. And the present is at the right-hand side of this picture. And so the 100,000-year cycle sort of indicates it's going to go back towards the next ice age. The external forces, the axial tilt, and the precision cycles also indicate the same thing. We would be expecting more ice on the North Pole, but in fact, there's less ice. So we're not in this normal cycle anymore. Now, why is that? And why is the cycle not enough? These cycles, these astronomical features, would not explain the enormous temperature differences we see between ice ages and non-ice ages, warm periods in between. The essential thing is that these astronomical features trigger two slow feedback mechanisms. And one of this is what is called the ice-albedo coupling, and the other is called greenhouse gas feedback. Ice-albedo coupling just means that in a cold world with a lot of ice on the surface, we have a very bright surface reflecting much of the sunlight, so it doesn't heat up as much, and this is a feedback mechanism. If the ice melts, then it warms, more ice melts, it continues to warm, and so on. And the same is true for the greenhouse gas feedback. More greenhouse gases in the atmosphere mean more warming and mean more greenhouse gases in the atmosphere because, for instance, water vapor evaporates from the oceans. There's also a carbon dioxide feedback. Now, the essential thing to understand is that together with these two slow feedback mechanisms, we can explain that, that curve over the last 400,000 years to 99%. So this is really the mechanisms that triggered past climate change. Now, what is different? We have put greenhouse gases into the atmosphere. And what you see here is the greenhouse gas emissions, carbon dioxide, in this case, between 1751 and 2002. And what I really want you to take note of is that the dramatic increase in emissions started at the end of Second World War. I'm sure you're aware of this, but from the point of greenhouse gases, this also means that we haven't been causing this problem for hundreds of years. This is a rather recent phenomenon that we've been observing. And more greenhouse gases in the atmosphere, because of this very close coupling between greenhouse gases and temperature, also mean that the temperature has changed, providing that the emissions also cause an increase in concentrations in the atmosphere. And that this is happening, you can see in this graph, which is essentially the one we had before, except that the carbon dioxide is now a separate curve, and it goes back 600,000 years. But what you see here is that at the very end, at the very right-hand side of the graph, you have this peak. So concentrations have moved from an area between 180 and 280 parts per million to 380 parts per million over the last century or so. And not only carbon dioxide, also methane and N2O have increased considerably. So there has been a change, and this change has consequences in temperature. What you see here is the temperature starting 200 after Christ, and it moves on to about the present. And what you can see is that the temperature is rather constant. Yes, there are those wobbles in it because the system is extremely complex and it's not a straight line. But on the whole, it's rather constant, and we have this large increase over the last about 100 years. And I want to show you these last 100 years, more precisely the last 131 years, in a graph by Climate Central that just documents what the measurements tell us about the past. And what you can see here is that there is a warming and a cooling. Whatever is blue is cooling, whatever is yellow and reddish is warming, and there's an up and down, but on the whole, continents tend to vary more, and they tend to become warmer. Then starting, especially now in the 90s or so, there's a real decided change. There is a real increase in temperature globally. So this is data. This is not a model, this is data. So we have experienced this climate change over the past, and we can see it in many other aspects. Just two examples from Austria. You can see here the days with temperatures above 30 degrees, so-called heat days. And if you look at Vienna here, for instance, then you can see that in the reference period 1950 to 1980, the mean was something like 9 days with temperatures above 30 degrees, the median, sorry, not the mean, in Vienna, and now we're up near 14 degrees, 14 days with temperatures above 30 degrees. The nights, it doesn't cool as much as it used to cool at night. We have a lot of nights with temperatures that do not drop below 20 degrees. So there is a change. You'll be tasting wine this afternoon, or this evening. Possibly it comes from this region of the Wachau in Krems. What you can see here is that the gris days that are essential for the quality of the wine, especially for the sugar content of the wine, for the two types of grapes, Riesling and Grüner Veltliner, that are the speciality of the Wachau. Well, it was too cold in the first part, 1970 to 1980, 85. Then it was ideal, and now it's too warm for these grapes. So people are thinking about shifting to red wine in an area that was traditionally white wine area. So there is a change, it's noticeable. Question is, how will it go on? Well, the pictures, this is Copenhagen diagnosis. It's basically same information that is at the base of IPCC graphs. You can see the constant over the past, the increase of about 0.8 degrees over the last 130 years or so, and the increase that is possible towards the end of the century. I want to show you another animation done by Japanese colleagues on what this extreme scenario would be. I'll go into the feasibility of the scenario maybe in a minute. So let's look at this. It starts again in 1950, and again the colors change according to the warming. When colors become red, then we're on 2 plus 3 degrees, yellow is more than 6 degrees, and white is more than 12 degrees. And you can see in the first few years not much happened. You can see a little bit in the polar region. And in the 19 years, in the 90s of last century, the continents become reddish. Mountainous areas react faster, as you can see when the Himalaya passes by here. And polar regions react faster. And now towards the middle of the century, the oceans have a warming of 2 to 3 degrees, and the continents are already closer to 5, 6 degrees, beyond 6 degrees, and the polar region is already beyond 12 degrees. And as time progresses at the end of the century, according to this scenario, we have a temperature increase of 5 degrees centigrade. Now this makes a huge change. Now, I do not think that any such scenario is a prediction of the future. This will not happen. There's many reasons why it will not happen. One is possibly because there's not enough fossil fuels to feed it. Another is, even if there were enough fossil fuels, changes would be so noticeable that I would think that people will start to react. If they don't, well, they will react in a different manner. We will probably have some sort of serious disruptions that also will limit this development. If we're talking about 5 degrees warming, this would mean, in terms of sea level rise, it would mean sea level rise on the long term, we're talking about thousands of years, of something like 70 to 80 meters. Now, this doesn't scare anybody because it's so long off and because we're all hoping that these 5 degrees will not happen. But even if we talk about the 2 degrees that are the political aim of where we're heading for, 2 degrees temperature increase means a sea level rise of some 40 meters in the long run. But you cannot stop it. Once you get into these self-supporting mechanisms, these positive feedback loops, then you can't stop the system. And this means even if we stabilize at 2 degrees, sea level will continue to rise until it reaches 40 meters. Now, if you think about what coastal areas are below 40 meters, you will find almost all of them are. 2 centigrades stabilization is not everything's fine. There's a lot of change involved in that. And this is the essential point, I think, that we keep losing out of focus, and that we don't really think of enough, that there is something which is called tipping points. Once we cross these tipping points, we cannot stabilize the climate. And the general agreement in the political arena now is that 2 degrees Celsius is the level at which we can still stop these tipping points. Now, in science, discussion is becoming louder and louder that 2 degrees is too much, that we really can have to stop at about 1.5 degrees because we can't stabilize climate beyond that. And 1.5 and 2 as well are both below the most optimistic IPCC scenario. So even if the fossil fuel situation is such that we will never be able to accomplish the A1, F1 scenario or any of those scenarios with strong temperature increase, even the lowest one are beyond the tipping points. So this is a reason why we cannot just discard climate change as of no relevance. Now, this has been talked about. 750 gigatons is what we still can put into the atmosphere in order to stay below the 2 degrees Celsius, with a 2/3 chance of really achieving that. Naki described this. I will not repeat that. What I want to show you, and why I think it's so important that we really discuss these absolute figures and not reductions by so and so many percent, as is so frequently done in politics, is that we're really talking about physics, and we're talking about an absolute amount of carbon dioxide that we can put into the atmosphere if we want to stay below the 2 degrees limit. Now, if we assume that we give the non-Annex I countries, which is countries in transition and developing countries, a chance to grow for the greenhouse gas emissions to grow by 3.5% per year, reach a peak in 2025, and then reduce by 7% per year. And this is a very, very ambitious program. It's not anything near what is happening at the moment. But if we assume that these countries will adhere to this kind of scheme of development, what is left for the industrial nations? Well, it's the blue curve. And that peak was 2010, and the decrease was infinite. So we're really up to a serious problem. There's 2 options we sort of have. One is try to adapt to global temperature changes above 2 degrees Celsius, and a stabilization of the climate, which we cannot reach beyond 2 degrees, so, or most likely cannot reach. So this is not something we can really enter into, this option. And the other option is to reduce greenhouse gas emissions to less than the 750 gigatons. And this, economists tell us, is impossible. Now I want to go back to one of the aspects that was discussed here. The one of these is physics, and the other is economy. And the physics is the top one. We cannot argue about the physical system of the climate. Once we embark on this, it just happens. So what we really have is only one option: to do some changes in the way we run our economies. Now, if you're not convinced that climate change is happening, and I think the same kind of diagram could be set up for peak oil, just look at the risk analysis. The climate hypothesis, we cannot decide here and now, and no individual really can decide, and even science cannot, in a strict sense of the word, decide whether this hypothesis is right or wrong. But we can decide whether we take action or we don't take action. And now if we get 4 squares, and if we look at every square and look at the worst possible that can happen in that combination, what is it that can happen if we assume climate change is happening, the hypothesis is right, and it's not. Climate hypothesis is wrong, but we take action as though it were right. Well, we have some impacts on economy. They might be negative. If we look at the worst possible situation, we have to assume that they will be negative, even though many people tell us, no, they will be positive. But at the same time, we'll save energy and resources. Now, if the hypothesis is wrong and we take no action, well, we didn't have a climate problem to start out with, so that's no difficulty. The problem of the resources will remain. If the hypothesis is right and we take action, then hopefully we can limit climate change to 2 degrees Celsius and limit the consequences of climate change. So we're sort of okay. But if the hypothesis is right and we take no action, then we have this temperature increase of whatever. In the long run, it will be very high, not because of greenhouse gases, but because of the positive feedback mechanisms, water shortages, extreme events, migration, tipping points, whatever. So taking the decision between action and non-action, in the case of taking action, there's no really serious problem involved with that. But if we don't take action, we do face a very serious problem. So no matter of whether you believe in climate change or not, no matter when one believes in peak oil or not, it makes sense to act as though it would be happening. Are there cheaper solutions? Are there cheaper solutions than to really change our economy and change our lifestyles? Well, there's some that are being offered. Nuclear power is repeatedly being offered. We have a lot of problems with nuclear power. We have safety and waste problems. But there's other problems as well. For the climate change issue, nuclear power will come too slowly. There will be some sort of fuel crunch if nuclear power really becomes an important part of the energy system. The alternative nuclear technologies bring us very close to plutonium arms, and the needs for surveillance in these technologies are a danger to democratic societies. So it's not a very attractive option. Geoengineering, I won't go into the details. One of the main reasons why I think geoengineering is not a solution is because there's other boundaries we're hitting. This graph you maybe know. It is a graph that shows the field where the global ecosystem is resilient. That's the green part in the center. And the impacts we have can be within this resilience part of the global ecosystem, or they are beyond. And climate change, for instance, is one that is beyond. The ecosystem cannot cope with what we have, the impacts we have made. But climate change is not the only one. You can see here the nitrogen cycle, you can see biodiversity loss, ocean acidification is getting closer to this border, so is the phosphorus cycle. So there's other boundaries we're hitting. And the geoengineering solutions will not solve any of these problems. So let's not waste time and money on solutions which only solve one of these problems, climate change, but do not affect the other problems. Theodore Roosevelt, 1907, said the conservation of our natural resources is the fundamental problem. If we do not solve that, it will avail us little to solve all others. And I think it would do us good to keep that in mind as we discuss solutions for our problems. And this is maybe, in tying into the discussion before, one of the commonalities and also the difficulties both climate scientists and ASPO has. We've identified the problem, we've discussed it, we've put it out, people have become aware of it. Nothing is happening, or not very much is happening. Scientists keep saying we need more details, but the details will not change anything in the basic picture. So the real problem, as I see it, is that we have to put out a view, give people a view of what can be better if we change. For instance, not talking about standard of living, but talking about quality of living, quality of life. I think quality of life can be improved by using less and fewer resources. And I think we need a positive picture of where to go in order to get people moving. Because, as was also said before, the fears of change and the extent of change that is implied in peak oil as well as in climate change are so daunting that people just prefer to deny the facts. Thank you for your attention.